the next chapter is the gaseous state. So what is a gas? So gaseous, gas is a state of matter. It has no definite shape or volume. Gases are highly compressible because the particles have large intermolecular spaces. When the pressure is reduced, gases expand to occupy the available space. Their particles move freely and rapidly in all directions. Gas molecules move randomly at high speeds, allowing them to mix completely and uniformly with other gases by passing through the intermolecular spaces. Because of the large spaces between particles, gases have much lower density compared to liquids and solids. Gas molecules collide with container walls, exerting pressure equally in all directions. Particles in a gas are in constant, rapid and random motion. The forces between gas molecules are very weak, which explains the large distances between particles and their free movement. So these are all properties of gases. Now, if we move to gas laws, we already studied before in our high school standard. Okay, so first is Boyle's law. It says that at constant temperature, the volume of a fixed amount of gas is inversely proportional to its pressure. So V is inversely proportional to pressure. So V is 1 by P when N number of moles or amount of gas and temperature both are constant. So we get V is K by P, where V is the volume and P is the pressure and K is the proportionality constant. So if we rearrange this one, we get PV is K, or PV is constant. So we can say that when temperature is constant, so when T and N are constant, we get PV equals to constant. So for isothermal process, later we will see in thermodynamics, for isothermal process, for fixed amount of gas, PV is constant. So the volume of the gas changes from V1 to V2 and pressure changes from P1 to P2 at constant temperature. Then according to Boyle's law, we can write P1 V1 equals to P2 V2, or P1 by P2 is V2 by V1. So when T is constant, if we plot P versus V, we get this kind of plot. And as we just discussed, so P is K by V, K times 1 by V. So if we plot P versus 1 by V like this one, so we get a straight line passing through the origin. So it is like y equals to mx plus c, the equation of a straight line. So we know equation of straight line is y is mx plus c. C is the intercept. Here intercept c is 0 in this case. So the slope gives k, and here y p is y and x is 1 by v. So if we plot p versus 1 by v, we get a straight line passing through the origin. Next, Charles' law, that is volume temperature relationship. It states that at constant pressure, the volume of a given mass of a gas increases or decreases by 1 by 273 of its volume at 0 degree Celsius for each degree rise or fall in temperature. For 1 degree rise in temperature, of volume increases by, so if we say this is Vt, is V0 by 1 by 273. So for T degree, if we increase the temperature T degree, we get V0 times T by 273. So initial volume was V0 and the final volume after T degree rise in temperature is V0 times T by 273, and if we rearrange, we get Vt, the final volume is V0 times 1 plus T by 273. Then concept of absolute Kelvin scale of temperature. When a graph is plotted at constant pressure between volume and temperature, a straight line is obtained. So if you see the expression here, so if we plot Vt versus T, okay, so V0 is the initial volume, okay. So again we get a straight line, but we get an intercept here. This is the intercept, and the value of intercept is V0 here. And the value of V total or the final volume becomes 0 when T becomes minus 273. So if we put the value of T is minus 273, we get Vt is 0. So you see volume goes to 0 here when T is minus 273 degrees Celsius. Okay. So when a graph is plotted at constant pressure between volume and temperature, a straight line is obtained. When the line is extrapolated, like here, the temperature at which volume becomes 0 has been found to be minus 273 Kelvin. This temperature is known as absolute zero temperature. So this is the absolute zero temperature, minus 273 degree Celsius. Then we discuss Gay-Lussac's law or pressure temperature relationship. This law states that at constant volume, the pressure of a fixed amount of gas varies directly proportional with temperature. So P is proportional to T when V and N both are constant, so P by T is constant. So if we again plot P versus T, since P is KT, K times T, so you get a straight line here, pressure temperature plot. Then comes Avogadro's law, this is volume on amount of substance relationship. It states that at a given temperature and pressure, the volume of a gas is directly proportional to the amount of the gas. So volume V is directly proportional to N when P and T are constants. So V is proportional, K is the proportionality constant, and here N is the amount of substance or number of moles. Now number of moles of a gas can be calculated as number of moles. We know that mass of the gas by molar mass. So if we divide it, if we divide the amount mass of gas we have taken by molar mass of that gas, we get the N or number of moles. So if we substitute the value of N in this expression of V, we get V is K times small m by capital M. Now if we combine all these laws that we discuss now, so Boyle's law says V is inversely proportional to P, or V is proportional to 1 by P when temperature and amount of gas is constant. According to Church's law, V is proportional to T when pressure and number of moles are constant, and according to Avogadro's law, V is proportional to N when constant P and T both are constant. So if we combine all these three, we get V is proportional to N times T by P, or PV is proportional to NT, or PV is proportional to nRT. This R is called the universal gas constant, and we know the value of R in different units like 0.082 in liter atmosphere unit, 8.314 in joule unit, and 2 in calorie unit, and so on. Then it comes. Then we discuss Dalton's law of partial pressure. So partial pressure means when we have more than one gases in the gas mixture. So we get partial pressure. So Dalton's law of partial pressure states that the total pressure exerted by a mixture of two or more non-reacting gases in a definite volume is equal to the sum of the individual pressures which each gas would exert if it occupies the same volume along a constant temperature. For example, if P1, P2, P3, etc. are individual pressures of gases known as partial pressure, then the total pressure is P1 plus P2 plus P3, etc. Suppose at temperature T, three gases are enclosed in the volume V, exert partial pressure like P1, P2 and P3 respectively. Then partial pressure exerted by gas 1, if we say that P1 is N1, means number of moles of gas, because as we just discussed that pressure is directly proportional to the amount of substance. So we get P1 is equals to your N1 RT by V. Similarly, P2 is N2 RT by V and P3 is N3 RT by V, where N1, N2 and N3 are the number of moles of first, second and third gas molecules. So the total pressure, we have to just add these three quantities P1, P2 and P3. So if we add them, we get N1 times RT by V plus N2 times RT by V and N3 times RT by V. So we get N1 plus N2 plus N3 times RT by V. So if we, on dividing P1 by P, so if we divide, so we know P1, what is the value of P1 we just discussed. So value of P1 is this. So if we divide this P1 by the value P we got here, So we get N1 by N1 plus N2 plus N3 RT by V times V by RT. So this they get cancelled. So this is nothing but the mole fraction of gas molecules A. So or X1 is called the mole fraction of gas A. So we get P1 equals to P1 by P equals to X1. So we get P1 by P is X1, or P1 is X1 times P. Similarly, for other two gases also we know we get P2 is X2 times P and P3 is X3 times P. Thus, the partial pressure of gas in the mixture is the product of its mole fraction and total pressure of the mixture. So, product of the total pressure times the mole fraction of that gas gives you the partial pressure of the gas. Next, we discuss Graham's law of diffusion or effusion. It states that under similar conditions of temperature and pressures, the rates of diffusion of gases are inversely proportional to the square root of their density. So, rate of diffusion is square root of density and is inversely proportional. So, 1 by density, and then you have to take the square root. So, Graham's law is also valid for effusion, that is when the gas in a vessel are allowed to escape through a small aperture or hole. Okay, so, this Graham law of diffusion is also applicable for effusion process also. Next, we discuss kinetic molecular theory of gases, and the postulates of kinetic molecular theory of gases are: all gases are made up of a very large number of extremely small identical particles. The molecules are separated, or molecules or particles are separated from one another by large distances. The empty spaces among the molecules or particles are so large that the actual volume of the molecule is negligible as compared to the total volume of the gas. So, we need to basically neglect the volume of each particles or gas molecules when compared to the total volume of the gas. Third point is says the molecules are in a state of random motion in all the directions during their motion. They keep on colliding with one another and also with the walls of the container, and thus change their directions. Fourth point is molecular collisions are perfectly elastic. There are no forces of interaction between the particles or molecules at ordinary temperature and pressure. The pressure exerted by the gas is due to collision of its molecules on the walls of the container. And the average kinetic energy of the gas molecules is directly proportional to the absolute temperature. This is a very important point. So, the average kinetic energy of the gas molecules, so higher is directly proportional to the absolute temperature. So, higher the temperature, higher will be the kinetic energy of the gas molecules. Now, we discuss kinetic gas equation. So, on the basis of the postulate just we discussed, if kinetic molecular theory, the kinetic gas equation was derived. Consider a cubical container of length L, this is the cubical container of length L, with gas molecules with mass m, and n is the number of molecules. So, we have capital N number of molecules there, and mass of each gas molecule is small m. Due to the influence of temperature, the gas molecules move in a random direction with a velocity v. You can see the gas molecules, they are moving in random directions with velocity v. The pressure of the gas molecules on the wall of the container, so pressure we know force per unit area. So, pressure of the gas molecules, so if we say this P is F by A is the area of the container. So, consider a gas molecules moving in x direction and hits the wall with a velocity Vx and rebounds back with the same velocity, because it will be experience a change in the momentum which is equal to your delta P is minus Vx, okay, minus Vx minus mVx, minus mVx minus mVx. So, you get minus 2 mVx, because the delta P is your change in momentum. So, it comes like final momentum is minus mVx minus initial momentum is mVx. So, this is final momentum. If we say Pf, this is your initial momentum, this is Pi. So change in momentum, if we say delta P, this is your delta P is your Pf minus Py, and then you get this value. Okay, so delta P is minus 2 mvx. How many molecules we have? We have n number of molecules in our system. So for n number of molecules, the value of delta P is your minus 2n mvx. The force is given by the change in momentum by time. So F is your delta P by T, because change in momentum by time gives the force. So minus 2n mvx by T, this gives the force. Now gas molecules hit the wall and travel back across the box and collide with the opposite face and hit the same face again after time t, which is given by this. So L is the edge length of the box, okay, length of the box. So T is your 2L by Vx, because it covers 2L distance in time t with velocity Vx. So if you substitute the T in the force equation, we get force of molecules is n mvx square by L. So we get F wall is your mvx square by L. So now the pressure P is given by this expression, force on the wall by area. So n mvx square by L to the 3. So now L to the 3 gives you the volume. So PV is your n mvx square. Since Vx, Vy and Vz are independent speeds in the directions, and if we consider the gas molecules in bulk, then they are equal. We consider both the values of Vx, Vy and Vz are equal. So we get average velocity, V square average is 3 Vx square. So if we substitute this here, we get PV is 1 by 3 mn and V square average. Here V square average is called the root mean square velocity. Then what is the average kinetic energy of gas molecules? Using the above relationship and gas laws, the average transitional energy of a molecule is half mv square average. The total energy of the whole gas container containing in molecules at a temperature T is given by this expression. So Ek is half mv, n number of particles we have, and for each particle we have the kinetic energy value half mv square average. So again the kinetic gas equation is PV is this that we just discussed here. Okay, so PV is this. Okay, so PV is 1 by 3 mn v square average. So PV is, now if you rearrange this one, 2 by 3 times 1 by 2 mn v square average. So this half m n v square is nothing but the kinetic energy of total kinetic energy of the gas molecule. Okay, so if we substitute this, we get PV is 2 by 3 key. If you compare this one, so we get we know that PV is n at t. So n at t is 2 by 3 Ek. So for what is the value of average kinetic energy or kinetic energy? Kinetic energy is 3 by 2 n at t. So the average kinetic energy per molecule, this is average kinetic energy when we have n number of molecules. So if we have average kinetic per molecule over dividing both sides by Avogadro number. So if we consider we have Avogadro number of molecules in our system, so average kinetic energy is 3 by 2. N we are small n we are considering 1 here, so we get 3 by 2 at t by Na, so we get 3 by 2 kBt, where kb is the Boltzmann constant and the value of kb is R by Na. Okay, so this is the average kinetic energy as for a single molecule. Okay, so that we get from kinetic theory. Next we discuss Maxwell-Boltzmann distribution of molecular speed. So molecules in a gas do not all have the same velocity, and a single molecule's velocity constantly changes due to collisions, typically in less than 10 to the minus 19 seconds. Because there are many molecules, their velocities vary widely, resulting in a broad distribution of speeds among the molecules. In 1860, James Clerk Maxwell calculated the distribution of velocities from the laws of probability. He derived the following equation for the distribution of molecular velocities. dnv by dn is 4 pi m by twice pi at t to the 3 by 2 e to the minus mv square by 2 at t v square dv. So in this expression, dNV is the number of molecules having speeds between V and V plus dV. N is the total number of molecules, and m is the molar mass, and T is the temperature in absolute scale. This relation is called Maxwell's law of distribution of speed. The ratio dNA by NaN gives the fraction of total number of molecules having speed between. So we have n number of particles among n number of particles, the fraction of the total number of molecules having speed between V and V plus dV. So if we plot number of molecules versus speed, we get this kind of plot. Now this plot actually we can expect from this expression. So you can see that, okay, so if we plot number of molecules versus this expression, it has one expression or one term, which is this one. Okay, this one decreases with increasing v, increasing velocity v, and this term v squared term, it increases with increasing v or velocity. So this expression it contains one term which is decreasing function of v and another term which is increasing function of v. So if we plot only number of molecules versus v square, suppose, okay, so we get, if we consider only v square, we get increasing function of v. This is increasing function of v. And then we have exponential term which is decreasing function of v. As v increases c in this direction, and n increases, the number of molecules increases in this direction. This is your decreasing function of v. Decreasing function of v or velocity. So if we combine these two, we get a curve which passes through a maximum here. So that's what we are getting here. If we plot number of molecules versus speed, it passes through a maximum here, as one can expect from this. So this relation Maxwell of distribution, okay, fine. So this is the plot. So this is called most probable speed. This is the average speed, and this is the root mean square speed. So important features of Maxwell-Boltzmann's distribution: the fraction of molecules with very low or very high speed is very small. So you can see the fraction of molecule with very low, very high speed here is very small, or very low speed is very small. The fraction of molecules possessing higher and higher velocities goes on increasing till it reaches a peak and then starts decreasing. So it is quite obvious here. You can see this is like this. This can be explained from this curve also, just we discussed. And the maximum fraction of molecules possesses a speed corresponding to the peak in the curve known as most probable speed. So this is the most probable speed. Now we discuss different types of speed. First we discussed most probable speeds, or VMP. It is the speed possessed by maximum fraction of gas molecules at a particular temperature. To find the most probable speed VMP, which is the maximum point on the curve, we differentiate equation 9, which is equal to 0, and then we make it 0. So we need to differentiate this one, and then we need to make it 0, because this is the most probable speed, because dNA by N is very high here, the maximum here. So if B, or we can say dNA V by N is 4 pi this, 4 pi, and then m by twice pi at T to the 3 by 2, m is the molar mass here, e to the minus m v square by twice at T, and v square m is the molar mass of the gas. So if we differentiate Fv with respect to v velocity and make it 0. So, if we do the differentiation here, we get 4 pi. So, if we differentiate this expression, we get 4 pi m by twice pi r t 3 by 2 e to the minus mv square r t, and for this one we get 2v, and then if we differentiate another v term here, we get another term here. So, if we make it 0, so either we get v equals to 0 or this, but v cannot be 0. So, we make 2 minus mv square by rt equals to 0. So, v square gives you twice 2 rt by m. So, v most probable, the most probable velocity, value of the most probable velocity is twice root over twice rt by m. So, higher the temperature, higher will be the most probable velocity for a particular gas, or at a particular temperature, higher the molar mass, lower will be the most probable velocity. Next, we discuss average speed. It is the average of the different speeds of all gas molecules. To calculate the average speed V average, we must integrate. So, we have to integrate it 0 to infinity V Fv dV. So, we get V average is 0 to infinity V, and Fv value we know if we substitute it here, and then we get V average is 4 pi m by twice pi r t to the 3 by 2 0 to infinity V3, and this term, and this is this integration we can get it from there, and then if we substitute everything we get the average velocity, which is 8 rt by pi m. So, this is the average velocity value. Okay, so again we can see that, okay, so average velocity increases as we increase temperature, and it decreases with increasing molar mass of the gas. So, okay, so after this we will discuss root mean square speed.